How does quantization error affect signal sampling? Imagine trying to capture a smooth flowing river in a series of snapshots. Each snapshot is like a sample of the river's height at a specific moment. Now, when converting that continuous flow into digital data, the process involves two steps: sampling and quantization. Sampling picks out the river's height at specific times, but quantization is where things get interesting. It rounds each sampled value to the nearest available level, which can cause some inaccuracies. This rounding is what we call quantization error. It's like trying to draw a perfect curve with only a few straight lines. Some details get lost. The bigger the difference between levels, the more error we introduce. If the voltage range of the signal is large but we only have a few levels, each step between levels is big, and so is the error. For example, if a signal swings from positive 7 volts to negative 7 volts and we only have 8 levels, each step covers 2 volts. The maximum error can be up to 1 volt, which is half of that step size. Now, if we increase the number of levels to 16, the step size shrinks to 1 volt, having the maximum error. This shows how more levels mean less error. When we add more bits to our digital representation, we double the number of levels, which halves the step size and reduces the error. This is why higher resolution systems produce more accurate signals. Quantization error appears as noise in the digital output, often sounding like a faint hiss or crackle in audio signals. It can distort the original waveform, especially in audio or image signals, making them sound or look less clear. The noise from quantization is usually random but can sometimes create harmonic distortions in signals like sine waves. The power of this noise depends on the size of the step. Smaller steps mean less noise. When the signal is much larger than one step, the error behaves like a small random noise added to the original signal. The signal-to-quantization noise ratio measures how much the original signal stands out from this noise. To reduce quantization error, engineers increase the number of levels, which means using more bits per sample. But this also means more data to store or transmit, so there's a trade-off. High-fidelity audio or precise control systems need more bits to keep errors low. Timing also matters. Sampling captures the signal at specific moments, while quantization rounds those values. Both steps can introduce errors, but sampling errors are related to how often we sample, while quantization errors depend on how many levels we have. In control systems and digital signal processing, managing quantization error is vital. If the error gets too big, it can affect the system's accuracy or stability. That's why choosing the right number of levels is a key part of designing effective digital systems. Understanding how quantization error works helps engineers make smarter choices about how to convert real-world signals into digital data, balancing accuracy with practical limits like storage and processing power.